Okay, so today we're going to be talking about inverse circular functions. We know what a circular function is, and now we're just going to be talking about the inverse of it. So those of you who are taking Math 103 concurrently with this are going to be at a little bit of a disadvantage here because you have not talked about, Josh, can you mute your mic, please? Because we haven't talked about inverse functions in college algebra yet. So if it seems like I'm going through fast, well, next week in college algebra, we'll hit it a lot slower. Recall that for a function f, every element in the domain corresponds to one and only one element in the range. This means that if point AB lies on the graph of f, then there is no other point on the graph that has A as the first coordinate. However, there may be other points having B as the second coordinate, since the definition of function allows the range elements to be used more than once. Well, if a function is defined so that each range element is also only used once, then it is called a one-to-one function. When I teach this slowly in college algebra, I always talk about how a function is like mapping people with their birth dates. It's possible for two different people to have the same birth date, but a one-to-one function is like people and social security numbers. Each person has one social security number and there's no repeats. So a function f of x is one-to-one if for x1 and x2 in the domain of f. If f of x1 does not equal f of x2, if x1 does not equal x2, then f of x1 won't eat f of x2. Equivalently, if f of x1 doesn't equal f of x2, then x1 won't equal x2 either. So no two inputs map to the same outputs. Say one-to-one correspondence. 1x, 1y, no repeats. Please note that the graph of a one-to-one function passes the vertical line test as well as the horizontal line test. If a function is one-to-one, then the function maps every x to one and only one y, and no two x values map to the same y value. This implies a one-to-one correspondence between the input and the output of this one-to-one function. So I must have left space here to draw my little diagram with people and social security numbers. So we've got this function f that maps people to social security numbers. And we know there can't be any repeat. Now, since there's this one-to-one correspondence, you could put somebody's name in a computer and look up their social security number, or based on their social security number, you could figure out their name because there's this one-to-one correspondence. That means that I could have this other function that takes social security numbers back to people's names. This function that maps the output back to the input of a function is called the inverse function. And we denote inverse with, it looks like an exponent of -1. It's not. It's just the notation that we use for inverse. So the inverse function of a one-to-one function is defined as yx such that xy is an element of f. All this means here is that x and y values get interchanged. So you simply flip-flop the x and the y in the ordered pair. Inverse functions have a couple properties. First off, the domain of the inverse function is equal to the range of the original function, and the range of the inverse function is equal to the domain of the original function. Our second property says that if you perform function composition with a function and its inverse, you will always get x. And we know that function composition is not commutative, so you'll see I have it in both orders, and either way, we're going to get x. And then lastly, the graphs of inverse functions are symmetric with respect to the line y equals x. So I got a diagram over here. The dotted line is y equals x, and I have two functions there, and we can see we have the mirror image on either side of that dotted line. How we go about finding the inverse function? Well, the first thing you need to do is verify that it is a one-to-one, because only one-to-one functions are eligible to have an inverse. Second, we want to take it out of function notation by replacing the f of x with y. Then we are going to interchange x and y. We will solve for y, and then lastly, we'll put it back into function notation by replacing y with f inverse. Now, we often restrict the domain of a function that's not one-to-one to make it one-to-one without changing the range. So, for example, we have f of x equals x squared. This is not a one-to-one function because it fails the horizontal line test if we look on its normal domain of all real numbers. But if I only take half of the parabola, if I restrict the domain to be just 0 to positive infinity, looking at only this portion, we do have a one-to-one function. In the remainder of this section, we're going to develop the inverse circular functions, and we will be restricting domains to do that. So let's take a look at our sine graph. I'm sorry, anybody have any questions so far? Okay, so let's take a look at our sine graph. Definitely not one-to-one because it fails the horizontal line test. So what we're going to do is we are going to restrict the domain of this function. We're basically going to select a portion as close to the origin as we can that is one-to-one. So if I just take this piece from negative pi over 2 to pi over 2, it is going to pass both the horizontal and vertical line test. So we can then say that y equals sine inverse, or this is just a different notation, and we only use this notation when we're talking about inverse trig functions. We might see it written arc sine instead. So y equals sine inverse or y equals arc sine means that x equals sine of y for some y value in between negative pi over 2 and pi over 2. So in other words, y equals sine inverse or y equals arc sine means y is the number, which is an angle, in the interval negative pi over 2 to pi over 2 whose sine value is x. So anytime we're finding an inverse trig function, we're finding an angle measure. And when we're looking by just pure definition of inverse sine, we only can give an answer between negative pi over 2 and pi over 2, because that's the one-to-one section of our graph. The range of y equals sine of x is negative 1 to 1. So using that property number 1 for inverse functions, we conclude that it will be the domain of the inverse function. And the range will be negative pi over 2 to pi over 2. So if we go back to our graph, and our our regular function is sine, we're restricting the domain to be negative pi over 2 to pi over 2. The range is -1 to +1. So then when we're going for the inverse, the domain of f inverse is going to be -1 to 1, and the range of our inverse function is going to be -π/2 to π/2. So we're just flip-flopping domain and range like we always do with inverse functions. Questions so far? So we want to find the exact value of y. And I want you to note the directions, because sometimes people, as we progress here, have issues when they're taking quizzes and exams on when are they using the pure definition of inverse and when are they using everything on the unit circle. When the directions are find the exact value of y, and they don't say on the interval 0 to 2 pi, this is where we're using the traditional inverse definition. So y equals sine inverse of -√3/2. Basically, the question is, what angle between -π/2 and π/2 does sine equal -√3/2? So that's what this question's asking, the notation's asking us. Okay, well, if we're between -π/2 and π/2, that's quadrants 1 or 4. It's telling us that sine has a negative value, so that means that we got to be in the 4th quadrant. And √3/2 is the long side of our 30, 60, 90 triangle. So x will be the short side, y will be the long side. Here we have a triangle. And we'll have a 60-degree reference angle. All we need to do is label what that angle is. And that'll be our answer. But you have to be careful, because we need to label it. It has to be something between -π/2 and π/2. You can't give me 300 degrees. You can't give me 5 pi/3. We would have to be -π/3 for our answer here. Because it has to be within this interval from -π/2 to π/2. Questions? And even if you plug this in your calculator, the calculator only ever gives a pure definition inverse answer. So if you plug it in, you're going to get, some weird decimal, whatever pi divided by 3 is, negative there. All right, let's try the next one. Let's find y equal to arc sine of -1. So here the question is, what angle between -π/2 and π/2 does sine equal 1? All right, well, sine only equals 1 at one spot, right here. Is that between -π/2 and π/2? Sure is, right? It's inclusive because we have our square brackets there. Y is going to be equal to exactly π/2. Questions at all on inverse sine, the notation, or anything like that? To get the graph of y equals sine inverse, we simply reflect the graph of y equals sine of x about the line y equals x. I say simply, but that's hard to do, to reflect that kind of wavy curve over a diagonal line like that. But that's where we get it. So I have a diagram there where I've done that, but then I zoomed in on just the part that we want. And then here's some kind of like a summary about the inverse sine function. The domain is from -1 to 1. The range is -π/2 to π/2. Sine inverse is increasing and continuous on its domain. Its x-intercept is 0, 0, as well as its y-intercept being the origin. And this graph is symmetric with respect to the origin, which makes it an odd function. So yeah, I guess you do need to know like all those facts. I think the domain and range are the most important ones. Your calculator helps you with domain because if you do sine inverse of 17, it goes error. But I could see us on our next test having a bunch of like short answer, multiple choice. We'll see what my math lab has for me to choose from this weekend. Questions at all about sine inverse before we go to cosine inverse? All right, I'm going to tell a similar story for cosine. So if we take a look at the graph of cosine, we see that it's definitely not a one-to-one function. But if I try to take that same piece that I did with sine, hey, that's not a one-to-one function either. So I need to select a different piece. This time, to get a one-to-one section, we're going to select from 0 to pi. We restrict our domain, we have this inverse function, or we have a one-to-one function. Oh, y equals cosine inverse, or y equals arc cosine, means that x equals cosine of y for y in between 0 and pi. So in other words, y is the number, the angle measure, between 0 and pi, whose cosine value is equal to x. So we can write that y equals cosine inverse is equal to cosine of y is equal to x. And we will be using this kind of flip-flop notation as we solve equations and things like that. We had the same thing up here with sine. I just didn't highlight it. So y equals sine of x is the same as sine of y equal to x. The range of cosine is -1 to 1, so that means that the domain of cosine inverse is going to be -1 to 1, and the range is going to be 0 to pi. Oh, all of our answers should be from the first and second quadrant when we're dealing with cosine. So it's different than sine. Sine, we're going from -π/2 to π/2. Cosine, we're going from 0 to pi. So let's find the exact value of y. Cosine inverse is only defined in quadrants 1 and 2. This number inside the parentheses is positive, so out of those two quadrants, cosine is only positive in the first quadrant. I see that 1/2 is the short side of my 30, 60, 90 triangle, so x is my short side, y is my long side, and we have a triangle with a 60-degree reference angle. Well, that's within quadrant 1 or 2 there, so we simply get that y equals π/3. That's the angle where cosine is equal to 1/2. Next, we have y equals arc cosine of square root of 3/2. Here, I'll write out the words like I did with sine. It's asking what angle between 0 and pi does cosine equal positive square root of 3 over 2. Well, cosine being positive out of quadrants 1 and 2, we got to be in quadrant 1. Square root of 3 over 2 is the long side of our 30, 60, 90 triangle. So that's going to give us a triangle with just a 30-degree reference angle. That angle's in our first or second quadrant, which we need it to be in. So y equals pi over 6. Since it's not, usually when the directions say, anytime it says exact value, we're looking for radian. That's how we know we want to be in radian. Questions so far? So it's kind of like we're going backwards on the unit circle. This time I'm giving you the ordered pair and you're giving me the angle. To get the graph of y equals cosine inverse, just like sine, we reflect the graph of y equals cosine about the diagonal line y equals x. We end up with this little funky graph here on the right. The domain is negative 1 to 1, just like it is for sine inverse. The range, however, is different. We're going from 0 to pi. Cosine inverse is decreasing and continuous on its domain. The x-intercept is 1, 0, while the y-intercept is 0, pi over 2. And this graph is not symmetric with respect to anything. Yeah, honestly, I don't stress over remembering all this so much about like, oh, which quadrant am I supposed to be looking in? Because I just picture the graph of sine or cosine. That I have to memorize. I have to know what that is. So if I just go back and picture that graph and then say, all right, where would the 1-to-1 section be? Then it tells me which quadrants I need. Questions at all about cosine inverse before we move to tangent? All right, well, let's take a look at tangent. Definitely not a 1-to-1 function because we have this shape that just repeats over and over again. But if we just took a single period of tangent, we would have something that's 1-to-1. So that's exactly what we're going to do. We're going to restrict the domain from negative pi over 2 to pi over 2 so that we get this one period here of tangent, and it's 1-to-1, and we'll use that for our inverse tangent. Y equals tan inverse or y equals arctan means that x equals tangent of y for y in between pi over 2 and negative pi over 2 and pi over 2. So just like before, we're looking for what's the angle between negative pi over 2 and pi over 2 such that tangent has whatever that number is. One thing I want to point out that is different here, for sine and cosine, the domain included the endpoints. But because we have these asymptotes at negative pi over 2 and pi over 2, we're looking at an open interval here. Here, this is a typo. This should be parentheses. All right, so let's talk about the domain and range a little more. The range of our tangent graph is all real numbers, so that means that the domain for our inverse tangent is going to be all real numbers. So we can do tan inverse of any number we want. We can only do we only can do sine inverse or cosine inverse of numbers in between -1 and +1. So let's find the exact value of y, where y equals tan inverse of 1. Our question is, what angle between -pi/2 and pi/2 does tangent equal 1? Tangent equals 1 when we have a 45, 45, 90 triangle. Right, since y and x will be the same, we need to be looking in quadrants 1 or 4, and it's a +1, so I need tangent to be positive, and that happens in our first quadrant. So we just need that angle for our y value, and that's going to be y equals pi/4. In our next example, we want to find y equals arctangent of 0. The question is, what angle between -pi/2 and pi/2 does tangent equal 0? Now, the only time that tangent equals 0 is when the y value is equal to 0 and the x value is anything else. Well, between -pi/2 and pi/2, where is our y value 0? Well, right here. We get y to be 0. Questions on our inverse tangent? You'll notice on your calculator, you do have inverse tangent, sine, cosine buttons. They're the second to your sine, cosine, tangent buttons. To get the graph of tan inverse, we do reflect the graph of tangent about the line y equals x. And we get this graph. This is probably the first graph you've ever seen that has two horizontal asymptotes to it. The domain is -∞ to +∞, while the range is only -pi/2 to pi/2. Tan inverse is increasing and continuous on its domain. It has an x and y intercept of the origin. The graph is not symmetric with respect to anything. And we have these horizontal asymptotes. The remaining three inverse functions are defined similarly. Honestly, we don't use them much. If it asks for secant inverse, I switch it into cosine and then do it with the cosine. So here's a summary, which is kind of crazy looking. As I mentioned before, I don't really memorize much of any of this. The graph of sine, cosine, and tangent tells me everything that I need to know. But I think that this is the most important part here, these first 3 columns. I'm never going to ask you to graph any of these inverse functions. This is the part we really need to know. What can I plug in to my inverse function, although your calculator will catch you on that, and what does it spit out? See, normally we would be having a non-calculator portion of the test where you would be doing all these inverse functions without the use of that, but you guys will have the advantage this semester. We'll do the 2-part test when we get to pre-calc. the inverse trig function keys on your calculator always give the proper quadrant for the definition of our inverse functions. So let's just practice using our calculator. I do not have these answers with me, so please make sure that you're popping them in your calculator. We want to use a calculator to find each value in decimal degrees. We'll round to the nearest thousandth. So we'll do cosine inverse of that number there. We should get something in between 0 and pi, or 0 and 180. Cosine's negative, so that tells me we should be somewhere between 90 and 180.
What should our calculators be set in, degrees or radians?
Well, it asked for degrees, so we want to put it in degrees.
Okay. Okay, I got something different now.
Did you get something between 90 and 180?
Yep.
What'd you get?
I got 97.67120.659.
Oh my goodness.
Or just 98 if you round up.
Okay, we're going to the nearest thousandth of a degree. So I'm sorry, can you give me that again? 90 what?
97.67.
That's only hundredth.
1.
All right, great. Everybody else get that too? All right, so let's find a cotangent inverse of 1.7670492. So this is a little bit trickier about plugging it into our calculator. Well, first off, we don't have a cotangent button. So I'm going to step you through kind of the long way so we know why we're about to do what we're going to do. I'm going to rewrite this using like this right here. We saw this on all three of them that we talked about, that we can rewrite it. So basically, if you have an inverse function, if you move it over to this side, it won't be inverse anymore. That's kind of what's happening. So I'm going to rewrite this. This is going to be the same as cotangent of theta equals this long decimal thingy here. We know that cotangent is 1 over tangent. Anytime now the variable we're solving for is located in the denominator, anytime that happens, we want to get it out. So I'm going to cross multiply and get 1 equals all of this tangent. Trying to isolate tangent, I'm now going to divide by that decimal, and we'll get tangent is equal to 1 over 1.7670492. Therefore, theta would then be tan inverse of this right here. So the reason that I did all that is to show you that when you're doing one of the other three trig functions, not our main ones, sine, cosine, tangent, if you're doing one of the other three ones, I didn't want you to make the mistake of saying, oh, this is going to be 1 over tan inverse of this decimal. when you switch to the other function, it's actually the reciprocal of the argument. So that's why I wanted to do out the algebra the long way, just so that you see why it is that we're not going to put the reciprocal on the outside of the function. The reciprocal goes in the argument this time. All right, now we're ready to plug it in our calculator. Get something in between 0 and 90 degrees.
$29.506.
All right, there we go. Questions? All right, let's try another one. Now we want to use our calculator to give each real number value. So the reason that we use radians so much in trig is because it's a real number. So when the directions say give a real number, that means radian. We'll round our answer to the nearest thousandth, and I already made a note for you and said make sure that you're in radian mode. That certainly will not be available for you on the exam. In fact, so I made a couple of my math lab exams last night because my virtual classes went live today. And please know, like, I went in and edited all the directions. So if it said, hey, use the Pythagorean identity to blah, 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 it doesn't say that anymore. It just says find the answer, as it would on my test. So just heads up on that. I don't want you to be surprised that some of the things that are given away on the homework will not be that way come exam time. All right, so let's use a calculator to give each real number rounding to the nearest thousandth. Y equals arc sine of 0.81926439. We should get an answer since this is a positive value and sine inverse is only defined in quadrants 1 or 4. We got to be in quadrant 1. So we should be getting something in between 0 and pi over 2. Yes, you're going to get a gross radian decimal. So we should get something between 0 and like 1.55, 1.6. Anybody get an answer?
So when it says arc sine, it just means the inverse of sine, right?
Yeah, it's just two different notations. Personally, I tend to use the little -1. I think maybe it's because it's less writing. And because I already knew inverse from college algebra, so I like to keep that notation, but it really gets used very interchangeably moving forward.
Okay, I got 0.96.
You want to go one more? 1,000?
Oh, well, it's just 0. It's 0.960.
Oh, okay. Anybody else
I
get that?
didn't get that.
I thought it would be something a little bit closer to 1 or on the other side of 1.
I got 0.611.
Well, that is not correct. Try again.
It might be your mode. Oh, it's radian mode, right?
Yeah, that's a radian. He got a radian answer. Just try it again. I like Amber's answer better.
I got 0.96.
I got 0.7306.
You are doing something weird with your calculator.
I
Make
just
sure you
did
got all those decimals in right.
I clicked sign, not sign inverse.
You click sine instead of sine inverse.
Yeah.
There you go.
Well, let me see if this actually works and if it's not my calculator being funny or if it's just me. Yeah, I got 0.948, which sounds a lot like everyone else's.
There you go. All right, so the next one is secant inverse. So we just saw in the previous one that what we're going to do is we're going to switch it to cosine inverse. However, we need to do the reciprocal of the argument. Now with secant and cosecant, if you do it incorrectly, it'll let you know because it'll be an error. We're going to get something in between pi over 2 and pi. Since the cosine value is negative, that pushes us into quadrant 2. Anybody have an answer?
$2.461.
Sounds good to me, because that's going to be something in between pi over 2 and pi.
Yep, same here.
Great. Questions, anybody, on calculator usage? I know it's hard. I would be normally walking around looking at your calculators, but we can still get through the calculator drama via Zoom. So if you're having any trouble with your calculator, please let me know. You can just hold it up to the camera. Okay. So now we're going to look at some function compositions involving inverse trig functions. So you'll notice as we kind of just scroll down the page, sometimes the inverse trig function is on the inside and sometimes the inverse trig function is on the outside. When the inverse trig function is on the outside, like this one here, we know that our answer is going to be an angle. Right? Because with function composition, we start on the inside and work our way out. So when whatever you have on the outside is the inverse function, this tells us that our answer is going to be an angle. When it's not an inverse trig function on the outside, our answer will be a real number. So like this one will be a real number. This one will be a real number. All right. So what we're going to do is we are going to start on the inside. And they're saying, what's arc cosine of 1/4? Now, if that 1/4 was a half, square root of 2 over 2, square root of 3 over 2, I would just grab the angle off of the unit circle. But since it's not one of our numbers off of the unit circle, what we're going to be doing instead is creating a triangle to reference. Now, the value inside our parenthesis is positive 1/4. And arc cosine is only defined in quadrants 1 and 2. So since that value is positive, that tells us that our triangle has to be in the first quadrant. And then I'm going to use SOHCAHTOA to label it. So it's kind of like I'm saying that this is whatever our angle theta. So SOHCAHTOA tells us adjacent over hypotenuse. So the inside part gives us the triangle. Now we want sine of that triangle that we just created. Sine is opposite over hypotenuse. So we're going to have to do Pythagorean theorem to get the opposite side. So 4 squared minus 1 squared. It's going to be 16 minus 1, 15. We get the square root of 15 over here. And then we want the sine of this triangle. The sine of this triangle, square root of 15 over 4. And that's our answer. You will most definitely be seeing questions like that on the exam. Questions on anything I did there? So use the inside angle to draw a triangle, assuming that the number is not right off the unit circle. And then you want to use the outside function and do that function of the triangle that you created. Let's try the next one. Now this one's a little bit different because the inside function is not the inverse. Oh, our final answer is going to be an angle. We will just evaluate what's here in the inside, and then we'll do the inverse of whatever that result is. So we're going to start by evaluating this. What is sine of 3 pi over 4? Right, just right off the unit circle.
Root 2 over 2.
You got it. So that simply becomes square root of 2 over 2, and now we want to do sine inverse of square root of 2 over 2. Remember that sine inverse is only defined in quadrant 1 and 4, and where I just drew it was in quadrant 2, so that can't possibly be my answer. I'm looking for a different place, within quadrant 1 or 4, where sine is equal to square root of 2 over 2, positive, and that happens right here in quadrant 1, again with a 45-degree reference angle. Exact value, so that means radian. So we're going to get that this is equal to pi over 4. And our answer is an angle like we said it would be, because the outermost function is an inverse function. Questions? Let's not start with all this. Questions, anybody? Before we get to the next ones, they're a little more complicated. Here, we want to find cosine of 2 tan inverse of -1. I've said over and over that our inverse function, it's just an angle. So like this right here is just, it spits out some angle. Say that's theta. So that means that what they're asking us for is cosine of 2 times some angle theta. Right, where theta is equal to tan inverse of -2. Oh, that means that we're going to have to use a double angle formula. I would choose to use the cosine double angle formula that just had cosine in it. So cosine of 2 theta is equal to 2 cosine squared theta minus 1. Two is not a number, or negative 2 is not a number just off of our unit circle. We never have answers that just spit out 2. It's always square root of 2 over 2, square root of 3 over 2, just square root of 3, things like that. So this here is not on the unit circle, so we're going to create a triangle. So we're going to do exactly what we did up here in this first one. All right. Well, tangent is negative, okay, negative 2. We know tan inverse is only defined in the first and fourth quadrants, and out of those two, tangent is negative in the fourth quadrant. I'm going to put my triangle down there in the fourth quadrant. Tangent is opposite over adjacent, so our opposite side, negative 2. Our adjacent side is 1. And what we need to find is 2 times cosine squared minus 1, and we're going to get the cosine from this triangle. And then we'll just plug it right into our formula. Oh, cosine is adjacent over hypotenuse, so we're going to have to do Pythagorean theorem to get our hypotenuse. That's going to be 1 plus 4. We get the square root of 5. Plugging it in there to 2 cosine squared minus 1. Remember that 2 cosine squared, that's the same as like 2, our cosine value squared minus 1. Oh, I did this backward. I just took the hypotenuse. Sorry. We gotta do adjacent over hypotenuse. There we go. I wouldn't waste my time rationalizing that 1 over square root of 5 because we're going to get ready to square it. And the square and square root will disappear anyways. So this is going to be 2, and then squaring the top, I get just 1. Squaring the bottom, I get 5, and then minus 1. 2/5 minus 1, we get a final answer of negative 3/5. That's a good problem. Questions? Usually when I teach this, I have a bunch of questions right about now. So anybody, questions? All right, well, when you run into them doing your homework, please make sure to contact me. All right, we got another one here. Our answer is going to be a real number because our outermost function is just a regular function. But you'll notice that inside the argument, I have 2 different inverse functions, and each inverse function gives us an angle. So we have an angle minus an angle. So this is like having tangent of alpha minus beta. where alpha is equal to cosine inverse of square root of 3 over 2, and beta is our sine inverse of negative square root of 3 over, negative 3 over 5. So we're going to have to use a tangent difference formula. On your formula sheet, tangent of alpha minus beta is equal to tangent of alpha minus tangent of beta over 1 plus tangent of alpha times tangent of beta. We're going to have to use cosine of cosine inverse of square root of 3 over 2. We're going to have to be able to figure out what tangent of that is. All right, we'll like make a little triangle. And then we'll make a triangle for the blue, for the beta, sine inverse of negative 3 over 5. And then we'll find the tangent of that triangle. And then we'll take those two values, plug it into this formula, and clean it up. So I'll start with the green. Cosine inverse is defined in quadrants 1 and 2. Cosine is positive only in the first quadrant out of those two. So I know my triangle is in the first quadrant. Yeah, I know square root of 3 over 2 is on the unit circle, but I think I'm just going to use SOHCAHTOA to find tangent rather than trying to think of what the tangent's going to be. Oh, cosine, that is adjacent over hypotenuse. And then we'll do Pythagorean theorem to find the opposite side because we're going to need that for tangent. So that's going to be 4 minus 3 square root of 1 is 1. So we can conclude from this triangle here that tangent of alpha, opposite over adjacent, or if we rationalize it, square root of 3 over 3. Now I'll do the same thing with the blue. Sine inverse is only defined in quadrants 1 and 4. Out of those two quadrants, sine is negative. In the fourth quadrant, our triangle's got to be down here somewhere. Using SOHCAHTOA, the opposite side is going to be negative 3, and the hypotenuse is going to be 5. We need tangent of this triangle, so we need the adjacent side. We're going to do our Pythagorean theorem. 25 minus 9 is 16. Square root of 16 is 4. And then tangent of this triangle is going to be our opposite over adjacent, negative 3/4. Questions on finding those tangent values? All right, now that we got them, we just plug them right into our formula. So that's going to be square root of 3 over 3 minus a negative 3/4 over 1 plus square root of 3 over 3 times a negative 3/4. And we just need to clean this up. So this double negative will turn plus. In the bottom here, I got a positive times a negative, so that's going to turn negative, and then our 3's cancel out, so we're looking at square root of 3 over 4. We want to simplify this complex fraction. We do so by multiplying each individual fraction by the LCD of all the fractions. So we're looking at denominators of 3, 4, 4, and 1. The LCD is 12. And we're doing some simplifying here. 3 goes in once, 3 goes in 4 times. So that gives us a 4 square root of 3. On the next pair, 4 goes in here once, 4 goes in 3 times, 3 times 3 is going to be a 9. In the denominator, we get 12 minus, simplifying again, 3 square root of 3. And that is fine with me as an answer. You do not need to rationalize that further. Questions?
How will we know it's rationalized to the extent you want it to be?
So if you have just one term in the denominator, go ahead and rationalize it. But if you have multiple terms, I'm fine, as long as you get rid of the complex fraction. Anybody else? Questions? All right, I really like these next two examples too. They're very similar to the first ones we did. We want to write each expression as an algebraic expression in U, where U is greater than 0. Clearly, U is not on the unit circle. So this problem here, even though it looks so weird with arc cosine and U and everything like that, it's exactly the same problem as this first one, sine of arc cosine of 1/4. We're going to create a triangle because what we were given is not on the unit circle, and then we're going to use SOHCAHTOA to get one of the other trig functions of the triangle that we've created. All right, so starting on the inside, here's our angle. Arc cosine is equal to U, and they told us that U is positive. Our arc cosine's only defined in quadrants 1 and 2, and out of those two quadrants, cosine is positive in the first one, so my triangle has to be over here. This is like U over 1, so using my SOHCAHTOA, adjacent over hypotenuse. And then I want tangent of this triangle, and tangent requires both opposite and adjacent. So we got to find the opposite side using Pythagorean theorem. Now this is a little trickier, I think, because there's no numbers in it, so you may need to do the side work. That 1 squared plus, I don't know, no, that's wrong. Sorry. Hypotenuse squared equals, I think I'm going to use y, I guess, because it's the vertical. Y squared plus U squared, and we're solving for y. And we get y to be equal to the square root of 1 minus U squared. Now I did do square root property here, so technically we get the plus or minus, but since we're in the first quadrant, we know it has to be the plus. So this is the square root of 1 minus U squared. For our final answer, we're just doing tangent of this triangle. Tangent is the opposite side over the adjacent side. And there's our answer. Questions? All right, why don't I give you guys a minute to do the next one. All right, so I started with my inverse sine of U over 4 to develop a triangle. U is positive, 4 is positive, so I knew my triangle has to be in the first quadrant. SOHCAHTOA tells me that sine is opposite over hypotenuse, so I labeled my opposite and hypotenuse side. Then I did Pythagorean theorem to get my adjacent side because I'm going to need that for cosine. Cosine is my adjacent side over my hypotenuse. We end up with a final answer of square root of 16 minus u squared all over 4. Please remember that you cannot break up a radical over addition or subtraction, so do not turn that numerator into 4 minus u. It's got to stay just as it is. Any questions? Again, that's a really nice problem. You will definitely be seeing something like that on your exam because, you know, that's not something you can just pop in your calculator and get the answer for. Tells me that you really understand what it means to be an inverse function versus a function and the composition of those two things. Well, that is the end of Unit 3, the end of the material that will be on our exam next week. So on Thursday, I will start Unit 4, which is solving trig equations. And then next Tuesday, we will not meet like this for class. You will just log on and take your exam. Your exam will be available from Tuesday at 12 a.m. and until Wednesday at 11:59 p.m. You'll get 2 attempts on the exam, but I will not award partial credit. You will only be able to review the exam immediately after you submit it. So that's the plan. I can take, you know, questions now on the exam, or I can take them on Thursday. But that's my plan.
So we just don't come into class on Tuesday.
Right, just like you wouldn't, you know, just like we wouldn't have lecture on an exam day, so this way you can use that time, because some people only have this time available to do schoolwork. So we're not going to have class. You guys will just dedicate that that Tuesday, Wednesday to taking your exam.
Is there any like timer to take the exam? Like you have 1 hour to take it?
Yep, it'll be 75 minutes just like normal, so just shoot me an email, you know. I'll have to manually take care of that myself.
Okay.
Yeah, maybe I'll make it 90 minutes. We'll see. I'll surprise you guys. Anybody else? Questions about anything, content or otherwise? All right. Well, then I will see you all on Thursday. That also means, though, that your take-home quiz and your MyMathLab homework is going to be due on, the test is Tuesday. It'll be due on Monday night. Let me know if you need anything. Have a great day, everybody.